Hello everyone. We are going to meet again for yet another topic. This topic is called as design for additive manufacturing. It is a part of the design for manufacture and assembly. Now let us go and have a look at the topic. Okay, so design for additive manufacturing is basically an attempt to work with the additive manufacturing in a much better manner, so that you can bring down the costs without sacrificing the strength of the product. It is actually an art, science, and a skill to design for manufacturability using 3D printers. It is different from the traditional manufacturing, basically because it empowers the engineers to create more intricate shapes and produce parts while reducing the weight of the component as well as the material consumption. As I told you earlier, the Dfam or design for additive manufacturing is a subset of design for manufacture and assembly. While the key factor that is important to consider for the design for manufacturing are planning, materials, processes, and standards, whereas here this design for additive manufacturing, the kind of planning that we do and the type of material that we choose and the process that we are going to use are totally different, or is a kind of another attempt where we are trying to overthink or think ahead before we try and then make a component using the additive manufacturing process. So, in general, like the design for manufacture, it uses complex geometry to bring down the performance goals. Basically, lightweighting, lattice design, internal channels for airflow, and etc. All that. They reduce the assembly complexity, consolidate the multiple parts. If multiple parts are there, join them into one. Reduce the development time, fast optimization iterations. As we know that additive manufacturing, we don't have the tooling is not much required, but separately we have the design for tooling also. Okay, like for casting tool for the regular manufacturing purposes, we can make tools out of this. Now, and the computer engineering is a must for design for additive manufacturing, because see, the 3D printing will not have any advantage on its own. Okay, if there is no if it is not performing the validation of the component. Dfam could be so complex that the traditional design process does not work. So places where there is no the other methods of manufacturing fails, Dfam could step in, and then any complex part or the assembly can be tackled by the Dfam process. CAE optimization provides a way to take advantage of the design for manufacturing freedom, and the CAE optimization tool is needed to generate the best design for meeting the performance requirements with minimum cost and minimum mass and cost. Okay, so while planning, consult with the manufacturing experts on your design so that you can lower the manufacturing cost. The next is to consider materials that are manufacturing compliant, which will be determined based on the process and the quality issues. Different processes have different costs and considerations, and for making them all into multiple parts or joining them into a multiple part that can be manufactured using the additive manufacturing. So we'll have to pull in the other experts and then try to bring out a proper design. Use of standard parts and components will reduce the inventory and its related cost. See, the different additive manufacturing technologies require different types of optimization. That is the underlying thing, because the additive manufacturing itself is around 7 or 8 different types are there. So each one will have their own way of design for additive manufacturing. Okay, so while applying the Dfam, you must avoid cost but you will have to consider what is the bill layout, what is the support structures that you're going to do, especially in the FDM process, what are the design guidelines. Okay, so what are the minimum and maximum feature sizes, what is the maximum aspect ratio that could be doing, then bridging the gaps and the overhangs, etc. what is the surface roughness that you are expecting, how the powder is going to be removed, what are all going to be the process parameters, what will be the layer thickness, what will be the laser spot size, okay, the thickness, the hat spacing, okay, and the laser power and scan speed, etc. How the powders are going to be spread. It also you'll have to think about the post-processing methods like the stress relief of the component. Then the part removal, how the part is going to be removed, thermal post-processing, then support removal or the machining, formal machining on the surface, etc., or the surface finishing. How you're going to inspect the component? Is it going to be a destructive or a non-destructive type of inspection? Whether the dimension and the dimensional and volumetric methods are being used, touch and contact, whether you are going to use the X-ray methods, etc. All these things have to be kept in mind. Now, some of the best practices of the guidelines that are prescribed to be kept in mind by the designers during the design of parts or products using the additive manufacturing are: first one, minimize the feature size. In Dfam also we talked about, unnecessarily don't make the component very complex, or unnecessarily don't make them into multiple parts. The first thing is that minimize the feature size. While these additive manufacturing process can produce small parts, there is always a limit to that. So results are best if the features are less than 0.006 of an inch in their smallest dimension. What will be the maximum wall height? For the straightness of thin walls, keep the maximum wall to our height to thickness ratio as 40:1. What will be the quality of supports? The optimum number of support structures should be 0 if that is possible. Okay, but if it is not possible, how are you going to compromise on that? Design the part and build its orientation to require as few supports as possible. Unsupported angles, for example, if it is a feature is 45 degrees from the horizontal and can be trusted to support itself, at a smaller angle, supports are likely to be needed. Unsupported overhangs, next layer can be larger than the previous layer, up by 0.020 inch. More overhang than this and support will be required. So you have to find out what kind of compromise are you going to do. Then unsupported bridge, the material stretching from one feature to the next can be up to 0.08 inch in span without the support. The font size, for text grown into part, use the Arial typeface of clarity with at least a 16-point font size. Why is because thin and thickness is not preferred. For example, you cannot use Times New Roman. Arial has a uniform thickness throughout. So other challenges are also definitely there during the design for additive manufacturing, especially when you make bulk parts, and then how are you going to fill up inside the thickness, etc. What type of lattice type is optimal for the performance? Can tool design optimal lattice instead of using a user choosing a type? Can the tool itself do it? Okay, or the slicer itself can do it. Okay, chopped lattice along the surface are not desirable because you don't have a bounding edge there. So there it is going to be a problem. So the outer surface has to be intact, and only the inner the area has to be made out of lattice structures. Auto resizing of a unit cell. Now that's the plenty of material is also there, and there are references. I have taken these kind of references. What I would like to summarize is that design for additive manufacturing is a growing and an opening field where the engineers or the designers tend to look at the best practices that can be adopted for the additive manufacturing process, and so that they anticipate earlier itself that what kind of design can be modified, how the design can be shaped, so that the additive manufacturing method of manufacturing that component can be very fruitful and then desired to its requirement. Okay, so thank you very much. We will meet again for another video. Thank you. I'll stop this.